All right, we are now recording. Everybody can see the PowerPoint, right? Okay, good deal. Okay, we're in Chapter 7, Applications of Integration, and now it won't advance, so I have to click on the slide to make it advance. Okay, 7.4 is talking about arc length and surfaces of revolution. Okay, now we did volumes of revolution. Now we're going to do surface area. So we'll find the arc length of a smooth curve. Now what do we mean by smooth curve? Can't have any cusp, can't have any corners, can't have any angles. Everything has to be nice, smooth, and continuous. They don't say continuous here, but that's what it means. Now what's another definition of a smooth curve? Well, first, the function has to be continuous, like I said, and secondly, the first derivative has to be continuous. Why is that? Because if it wasn't, if it's coming down here at a -1 and then suddenly goes to a +1, that's not a continuous and it's not a smooth curve. It's continuous. The curve is continuous, but the first derivative is not. Okay, and then once we have the arc length, we'll take that arc length and revolve it around your axis of revolution and have a surface of revolution. So that's where we're heading. Let's see if we can get there. We'll start with arc length, and this is on, if you aren't there already, Chapter 7, Applications of Integration, 7.4 arc length and surfaces of revolution, on page 474 in your text is where we're beginning. Now, definite integrals are used to find arc lengths of curves and the areas of the surface of revolution by doing something fairly similar to what we did, kind of the shell method-ish, but not quite, with arc lengths. In either case, an arc, which is a segment of a curve, okay, now the curve could be a straight line, that's okay too, is approximated by a straight line segments whose lengths are given by the familiar, I hope they're familiar, distance formula. Distance between any 2 points, x1 and y1, is the difference in x's squared plus the difference in y squared, the square root of that. And that's the good old Pythagorean theorem. If your delta x is like this, your delta y is like this, then to get from here to here, you do this squared plus that squared equal that squared. Then take a square root, and there's a distance of your, that's your distance formula. Now, a rectifiable, boy, what a word there, curve, is one that has a finite arc length. Okay, now what do we mean by that? It can't be going to infinity. Sort of like a tangent function at pi halves, just keeps going and going and going. That's not rectifiable. That doesn't have a finite arc length because it keeps going and going and going forever. So it needs to be something that has a finite arc length. Okay, that's called a rectifiable curve. You'll see that a sufficient condition for the graph of a function f to be rectifiable between the points A, that's on the x-axis, f of a, that's your y value at a, b, and f of b, which is the y value when x is equal to b, is that f prime be continuous on a to b. And that's what I was talking about. If the first derivative is not continuous, as in you have either a disconnect or a point, a cusp, or anything such as that, first derivative is not continuous, so that would not be a rectifiable function. Such a function is continuously differentiable on the interval a to b, and its graph on the interval a to b is what we then define as a smooth curve. Not only does the function have to be continuous, the first derivative has to be continuous. Okay? Now, let's get back to what we mean by arc length. Consider a function y is equal to f of x that is continuously differentiable on the interval a to b. You can approximate the graph of f by n line segments whose endpoints are determined by your partition. A is equal to x0, the first of those, and then you have that being less than x1, less than x2, less than x3, less than x4, all the way up to x sub n. And x sub n will be your b. So there's your interval from A to B. So this time, and I'm going to kind of fill in the blanks, they show one of these, but I'm going to try to show a few more of them. Okay, and I even got the right color. The line that goes from here to here, that fits pretty nicely. This one, you see, deviates a little bit. This one, if that was your last one, then it would deviate a bit more. Now that's not a straight line, but just imagine it is. Okay, but you probably had some more points in here. The more points you had in here, then the better you are. The more x's you had in here, the better your fit would be. Okay, now so we're approximating by this. Now that's obviously going to underestimate the arc length of the curve, which is the actual, if you had a flexible tape measure and could put it right along the curve, that would be the arc length. What you're doing now is measuring from this point to that point to that point to that point using a straight edge. Okay, not going to quite give you the same value. Okay, this is the arc length, and they named that S, the arc length of the curve from A to B. The approximation is this, the straight line, shortest distance between 2 points, straight line approximation between a series of, in a partition. You have a x sub 0, which is your A, x sub 1, x sub 2, x sub 3, x sub 4, x sub up to x sub n, and that happens to be your B. So you're doing the arc length between A and B. This approximates it, what that real value is. Okay, and I bet you you know what's coming, but they're going to drag it out for a while. By letting your delta x sub I, that would be this right here, the delta x, this would be delta x sub 2, because it's y2 minus x2 minus x1. That's your delta x sub 2. Here's your delta y sub 2, and this then would be the approximation of the arc length. Okay, we're going here. So delta x sub I would be x sub 2 minus x sub 2 minus 1 was x sub 1. Delta y sub 2 would be y2 minus y1. That's exactly what we showed here. Okay, then you can approximate the length of that little s, the arc length, to be the summation of all those lengths, straight line segment lengths, the square root of, and here's your good old distance formula, x sub 2 minus x sub 1, or x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. Take a square root of it. That would be that arc length, that straight line distance. Sum up all those as I goes from 1 to n. Okay, well, what does that produce? This is your delta x sub I. That's your delta y sub I, square root of that. Now, here's where the trick comes. Okay, what they're going to do here is divide everything by well, not quite, close to it. They're going to get there in a minute. Well, they're going to multiply the second term by delta x of I squared over delta x of I squared. They did it separately, but that's exactly what they did here. Okay, then they're going to factor out that delta x of I squared out of a square root, meaning just delta x of I. And what that leaves you is 1 here, because that one factors out, and then you just have dy delta y sub I over delta x sub I squared. What in the world does that look like? As you take a limit, as let n go to infinity, your interval's getting smaller and smaller. This is a dy dx. That approximation appears to become better and better and better as your norm for this partitioning is going to 0, n is going to infinity. This is what you expect here. And this would be going, that would then become an integral from a to b of the square root of 1 plus f prime squared dx. That's exactly what you get. So here's the s would be the actual arc length, would be what you get as a limit, and the norm is going to 0, meaning n is going to infinity, of this summation of 1 plus this thing, same thing we had before. Because f prime exists, remember that was a given here, for each x in the interval, it had to exist. It had to be continuous. The f prime had to be continuous, so it does exist for every x in that interval from a to b. So certainly between x sub I minus 1 and x sub I. It exists everywhere. The mean value theorem guarantees there is some c sub I in that interval x sub I minus 1 to x sub I, such that this thing right here is exactly your derivative. So this thing in the limit becomes that. Okay? F prime at c sub I. It is exactly that. Okay? From the mean value theorem. Okay? Because f is continuous, f prime is continuous on that interval a to b, it follows that the square root of 1 plus f prime squared is also continuous. Okay? And therefore integrable. Okay, does that mean it's going to be an easy integral? No, it doesn't guarantee that at all, but it is integrable on a to b, which implies then that this limit becomes that integral. The integral from a to b, that's your summation here, going from the first endpoint to the last endpoint, of square root of 1 plus f prime of x squared under the radical times your dx. That s is called the arc length of f between a and b, same thing we showed in the slide earlier. All right, that's the theory. Oh, and here's the definition. Let the function y is equal to f of x represent a smooth curve. Okay, that means no corners, no cusps, no gaps, no breaks, no discontinuities, a smooth curve on that interval from a to b, enclosed. The arc length f between, the arc length of f between a and b is then given by s is equal to that integral of from a to b of the square root of 1 plus f prime squared dx. Okay? Similarly, for a smooth curve that your x is a function of y, this is y as a function of x, the arc length of g, that g of y, between y equals c and y equal d would be the s, the arc length, is equal to the integral from the lower limit to the upper limit, c to d, of the square root of 1 plus g prime. Now that g prime is dg dy, okay? G d dy, not g dg dx, but dg dy, function of y, squared dy. Same thing, you're just exchanging your variables. And totally. Okay? Now, whoa, hit the wrong key. Sorry about that. Go back and hit the right key. All right, here's example 1. Now this example, oh, and by the way, time out for a moment here. There was a little blurb on the page 475 on Christian Huygens, Dutch mathematician. Christian Huygens invented the pendulum clock. James Gregory, a Scottish mathematician, both made early contributions to the problem of finding the length of a rectifiable curve. So there's two potential paper topics. Who in the world was Christian Huygens? Who in the world was James Gregory? Or another couple might be, how did they proceed in doing this? What was their process? Maybe also who uses it? You know, why were they doing that? Who needed to know that? So there you could come up with several different paper topics. Hint, hint, hint. Get working on your papers if you haven't turned them in already. I think I've only received maybe one from this class, so please don't forget about your research paper. Now, There's also, before example 1, you'll see in your text on page 475, for further information to see how arc length can be used to define trigonometric functions, there's trigonometry requires calculus, not vice versa, and that's in UMAP modules, whatever that is, okay? The author, I'm not going to try to pronounce his name, Yves Nivegelt or something like that. Okay, so there's another source for a paper. You have to go outside the book to get it. This little blurb on Huygens, that can't be your source, but that can give you ideas for where you find other sources. Okay, so let's do example 1. Find the arc length from x1 to x1y1 to x2y2 on the graph. Oh man, this is not a number in sight. Not a number here, not a number here, not a number here. We're just going to find the arc length from this point to that point for this function. Well, from what we just said, okay, here's how we're going to proceed now. If you think about it, what's the first thing you've got to do? Take a derivative. Okay? All right, so let's do that first. Your f of x, if I can find my pen, here it is. If f of x is mx plus b, f prime of x is equal to what? M, right? This is to the first power. 1 times m is m. Drop that to the one integer, that would be x is 0, which is 1. Derivative of b is 0. There's your derivative. F prime is n. Okay? What's the next thing we're going to do? We're going to square that derivative. If I can get my pen to show up. There we go. Well, I know why it's not. Okay. We're going to square it. So that's the next thing we do. F prime squared is simply m squared. Got it done. What's the next thing we're going to do? Add 1 to it. Okay? So what we wind up with is 1 plus m squared. What's the next thing we're going to do? Take a square root of it. Okay? So we'll take the square root of 1 plus m squared. Okay? And then we put that, we put that in our integral from, and these are the limits of x. So it'll be from, okay, I don't know what's making those noises. Let me just check and make sure somebody's not trying to come into class. I don't see they are. My guess is I'm getting emails, which is very annoying that it makes those noises. Do y'all hear the ding when I hear it? Oh, you didn't? Okay, well then I won't quit griping about it. I thought it was something that was interfering with what you were doing too. Okay, so we're going to integrate from x1 to x2 of the thing that we had here, dx. So here we go. I thought we would go. It won't advance till I click on the screen. There we go. So what we're going to do is integrate this thing from x1 to x2 dx. Okay. Now, it's a little disingenuous to put it like this, but what we're going to do, I think, is go back and change this, what your m is. So what is your m? Your m is y2 minus y1, oh, that's not y squared. Let me find my eraser if I can get it down here somewhere. Okay. So nice, I found that. y2 minus y1 over x2 minus x1. This is almost turns into an exercise in futility. Okay, but let's do it. So let's write that in here. this will be the integral from x1 to x2 of the square root of 1 plus, and then we've got to square this and square that. Okay, so this will be y2 minus y1 squared over x2 minus x1 squared. And then you got your dx out here. Okay, well, let's fix that up a little bit here. Let's put this, I don't know why they do this, but they do. Okay, all right, we're going to work on that a little bit here. If I can get my pen to show back, there it is. Okay, the square root of, now we're going to put it over same denominators. So this would be an x2 minus x1 squared plus a y2 minus y1 squared all over this same denominator, x2 minus x1 squared. But guess what? That's a perfect square inside a square root, so you can take that out. So this will be the integral from x1 to x2 of, I left off my dx here. Okay, of let me make sure I'm not making this any worse than it needs to be. Yeah, okay. At some point here, and I would have done it earlier, but I'm trying to do it the way they did. Okay, I think this is the point. In fact, I didn't even need to go this far. These are all constants. These are all given. Okay, they're values. I would have done this right up here, but they didn't. So I'm trying to do what they did. So this is just a constant. That could come outside the integral. Okay, I'll leave it inside for now. In fact, they leave it in this form, but since I've already written this, I'll do it in this form. This will be x2, well, wait, I'm taking the derivative. This constant will then be times x. Okay, but it's evaluated. Okay, x2 minus x1 squared plus y2 minus y1 squared. Now this is all inside the integral over x2 minus x1 squared. Okay, times x. Okay, evaluated from x1 to x2. This is that x. Okay, now I think I will do what I was planning to do earlier. This is the square root of x2 minus x1 squared plus y2 minus y1 squared. That's all under the radical. Okay, because this is a perfect square, that can be pulled out. x2 minus x1. No longer squared because you took it outside the radical. Okay, but then you evaluate this x from, so this is all your coefficient in front, that's just a number, x evaluated from x2 to x1, that would be x2 minus x1. Well, guess what? These two cancel out or divide away. Okay, well, what do we have here? This is your link between the 2 points. That is your distance formula. So what is the arc length between those 2 points? There it is right there. It's the distance between the 2 points. Because this is a straight line. That's a linear function. And the shortest distance between that is your arc length. So they went to all that mess just to show that the The arc length between these 2 points on that curve, and that's a straight line curve, is the distance between the 2 points on the straight line. That is your distance formula. And that's why I said this is almost a ridiculous problem. I guess it was nice or necessary or something to do, but I really don't see why. It was a lot of writing to get almost nothing. So let's see how they do it. The F prime, just like we did, was M. Okay, and the M from up here, we know, whoa, here comes Ashton in. So I think, ding, 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 we have perfect attendance today. Except I've lost my pen. Okay, and I'm stuck on my cord here. Okay, hold on. Ashton's here, perfect attendance. Howdy, way to go. All right. We're just doing example 1 we're in chapter 7, applications of integration, section 7.4, arc length and surfaces of revolution, on page 475, example 1. We did it on the board, and now we're watching them do it, hopefully about the same way. What it is find the arc length between these 2 points on this graph. So you know these 2 points are on that line somewhere. Not a number in sight here. We're just doing strictly by letters here. Well, the first thing we do to find the arc length formula, I can't get it to retreat, but here we go. There's your arc length formula. Arc length S is equal to integral from first value of x to the second value of x, between those two things, square root of 1 plus f prime of x, the first derivative of the function f, that function here, but then you square it all under the radical dx. So that's what we're doing. First thing we do is take the derivative. We did. And that comes out being m. But we know the slope between 2 points on a straight line is y2 minus y1 over x2 minus x1. Okay? So we're going to take that f prime and we're going to square it. Okay? Square this thing. Put it under a radical. Add 1 to it under the radical. And go, your arc length is from x1, that's your first x value, to x2, the second x value of that function, 1 plus the derivative of that function squared under the radical. Okay, that's your formula. Okay, so let's fill that in. Your x is going from x1 to x2, the square root of 1 plus y2 minus y1 over x2 minus x1 in parentheses squared. That's your f prime squared dx. Oh, I didn't know they did it exactly the same way. Yeah, I guess they did. I hadn't realized that. So what they did is, since this is over that square, this squared over that squared, let's put this squared over itself squared, which would be 1. So x2 minus x1 squared over x2 minus x1 squared would be the 1, plus y2 minus y1 squared over x2 minus x1 squared. And that would be a new way to express this. Okay? But remember, these are all constants. So basically, this whole thing could come outside the radical. Okay? And that just leaves your integral of dx. Well, the integral of dx is x. So it's this constant times x evaluated from x2 to x1. Okay? Well, we're going to plug in x2 here, minus x1 for that, all times that. And what that gives us is this. I don't see why they carried it around so far, but here in the denominator, you have a square root of a perfect square. So that can come out of the, and it did. They just made it disappear. When that comes out, your denominator becomes x2 minus x1, because the square root of a square, both of them disappear for the denominator. Stay in the numerator. And then this will then divide out with that, and that just leaves you with the distance between the 2 points. Well, what is the arc length along a straight line between 2 points? It's the distance between those 2 points, and that's what they're trying to show, which is the formula for the distance between 2 points in the plane. And if they were on that line, f of x equal mx plus b, those 2 points are on the plane, then that's the distance. That's your arc length, is that distance formula. Okay? Now, again, it almost seems like they were going around their elbow to get to the ear, but they got there. Okay. Now, that was the easy one, except they didn't have any numbers to make it a little easier. They're skipping examples 2, 3, 4, and 5. So let's go to our white page, and we'll do examples 2, 3, 4, and 5. Any questions before we leave that? All right. Now I've still got a little bit of housekeeping to do here. Let me move my taskbar, which I don't think you can see, but it blocks part of my white page, so I can't write on it. And then I'm going to move my white page as far to the left as I can. And you might say, why? Well, I'll try to give you an idea why, because I don't think you can see it. If you ever watch any of our videos, once I've recorded this on Screencast-O-Matic and loaded to YouTube, you see that over here there's a column of me and all 4 of your names here. Okay, so that's blocking my white space. So if I scoot my white space as far this way, scoot your names as far that way, then I can have more white space to work on. So that's what I'm doing. If you've ever wondered what is he talking about, that's what it is. Now, I'm sorry, I meant to point this out before. I think I will go back and do it. I think this will stay where it is. Let's go back here to this, and I don't know why they keep doing things like this. If you think about this, remember, here's the formula for arc length. Now, think about this for just a moment. You've got to come up with a function that when you take its derivative and then square that derivative and then add 1 to it, you get something that is ideally a perfect square. That's a pretty tall order to get. And even if it isn't a perfect square, it needs to be something you can integrate. Okay? Now, I know we said it's the smooth curves, it is integrable, but guess what? These things can get really nasty really quickly. Okay? So, what I'm getting at, don't be surprised to see some of these functions being really weird functions. You say, why would I ever come across that function? Well, the reason is they're trying to get a function that when you take its derivative, square it, add 1 to it, and then take a square root, you can integrate it. So they're trying to be nice to you, is what the answer is. And you may not think it. You may think they just came up with the weirdest formula imaginable, but that's why they came up with it, so you could integrate it and not have to do a numerical integration or something else like that. So let's see if I can get the whiteboard to come back. Yeah, it's in its place. So that's all my spiel on that. So let's do example 2. Find the arc length of the graph of, and you talk about a weird function here, y is equal to x cubed over 6. X cubed, that's supposed to be a 3, over 6 plus 1 over 2x. On first glance, you'd say, he must have stayed up at night coming up with a thing like this. On an interval, 1/2 to 2, okay? And even that, they've used some limits that'll make it somewhat easier for you, as shown in the figure. Now, I'd rather not draw the figure, so I'm just going to show it to you, Okay, now some days my picture doesn't show up here. Today it is. There is what that weird looking curve looks like. And they're only going from 1/2 to 2, so they picked a nice smooth, and the whole curve is smooth. Up here you see x can't go to 0 because you have 1/2x there. So you have a vertical asymptote here as the y-axis. You can't go too close to that. So they started at 1/2, good deal, good thinking, and then go here. And this seems like it goes forever because your x cubed over 6 is going to completely swamp your 1/2x for larger and larger x's. Okay, now I just did all that and lost my pen. Okay, now how do we proceed? Well, how did we proceed before? First thing you do is now I hope you don't mind if I use y prime rather than f prime of x. I'm going to do that. It's easier to write. Y prime, you take a derivative. What's your derivative of this? 3 times 1/6 would be 1/2 x squared. Okay? Now, I don't know if you do this in your head. I'm going to rewrite just this term to be 1/2 of x to the minus 1. Okay? That's exactly what this is. It's just written in a different form. This is far easier. Now that's not x minus 1, that's x raised to the minus 1, but I was getting near the top of my whiteboard and I can't write up there. Okay? So this is the derivative of that would be a minus 1/2. You do the exponent times your coefficient. Minus 1 times 1/2 is minus 1/2 times x to the, and drop that by 1, and that becomes minus 2. Oh, that doesn't look nearly as bad as I thought it might. Okay? That's why they chose such a weird function for you to begin with. What's the next thing we're going to do? We're going to square that. Okay? So y prime squared is going to be, okay, square the first term. That would be 1/4 x to the 4th twice the product of the two terms. So the product of the two terms would be 1/4, just 1/4, okay, minus 1/4, okay, because x squared times x to the minus 2, it's just 1. That's x squared times 1/x squared, that's just 1. So that's going to be a minus 1/4. That's your middle term, minus 1/4. Amazing, huh? Okay, and then square the last term. Oh, wait, that's not right. It's twice that product, and twice 1/4 is 1/2. So that is a 1/2. Sorry about that. I knew things weren't looking good. Okay. Twice the product of the two terms. Okay, and then square the last term. Well, that would be a plus 1/4 x to the minus 4. Now I'm going to leave it in exponential notation because it's a little easier to work with. Okay, now the next thing I've got to do is add 1 to that. Remember, it's 1 plus y prime squared. So when you add 1 to this, that's going to be adding 2/2 to it, right? What do you get then? You have 1/4 x to the 4th. Now that becomes minus 1/2 plus 2/2 would be a plus 1/2 plus 1/4 x to the minus 4. Okay. Now, what in the world are we going to do with that? We got to take a square root of it. Okay. But I want to point something out to you. Remember when we squared this, we got this thing right here. This thing looks a lot like this, only it's got a plus there. Where did the plus come from? That's from here. So my contention is, and it's true, this is the square root of 1/2 x squared plus 1/2 x to the minus 2 squared. Okay, check that and see. Square this, you get 1/4 x to the 4th, twice the product here. The product would be 1/4. Those two multiply to be 1. 1/4 twice that product will be 1/2, and then this squared will be that. Sure enough, that is a square root of a perfect square, and therefore we can lose the square root and lose that. So our integral here from 1/2 to 2 of all we got left, and this is the arc length, all we've got left is 1/2, because when you undo the square root, square is 1/2 x squared plus 1/2 x to the minus 2 dx. Okay, now I have a real tendency to want to take that 1/2 outside, so I'm going to do that. Okay, now we're just going to be integrating x squared, which is x cubed over 3, plus, we already took the 1/2 outside, so this will be, antiderivative of that would be, increase that by 1, okay, and that makes it a -1, divide by that -1, so that changes this plus back to a minus. Now let me get my eraser here and change back to a minus. Okay, minus x to the -1, or 1/x, you could say, and that's evaluated from 1/2 to 2. All right, so the 1/2 out front. The rest of it's just math. Okay, kind of messy math, but math. Okay, well, first you have 2 cubed, which is 8/3. So that's the first term, 8/3. Okay, minus 1/2, because this is x, 1/x here. So that's minus 1/2 minus a 1/2 cubed. Well, that would be 8. Wait, let me see. Yeah, minus 1/2 cubed would be, I'm pretty sure that's 8, because it's, no, wait. It's 1/2. It's 1/8. So that would be a minus 1/24. Okay, because 1/2 cubed is 1/8, and 1/3 times 1/8 is 1/24. But that's a minus. But then it's a minus here, minus from down here, minus from up here, so that makes that a plus. And then this is 1/x, and 1/1/2 would be 2. Okay, that's where I knew I got it. Okay, now the rest of it is math. Okay, messy math, but still math. So let me pull my 1/2 out, keep it out there where I want it. Okay, and then here we're going to have least common denominator, and that looks to be 24, right? Well, 3 will go into 24. 8 times 8 times 8 is 64. Minus 2 will go into 24, 12. Minus 1 plus, you could write it as 1. That would be 48. 2 would be 48 24ths. 48. Okay. Now, 64 and 48 is 112. Minus 12 would be 100. Minus 1 is 99. Okay, so it's 1/2 of 99 over 24. I hope I'm doing this right. And I happen to know that 3 will go into both of those. So that would be 33 over 8. So that gives me 33/16, I think, is the arc length of that curve. Now if you look at that on your graph, you see that's going to be something greater than 1. This certainly is. This is a little bit greater than 2. And looking at that graph, you think, yeah, that looks reasonable. Let's see what the book said. 33/16. Good for them. Okay. Now, they went to great lengths to find a weird function that when you took its derivative, it really looked less weird. Then when you squared it, it got a little weirder, but rather bizarre. Added 1 to it, and it came out looking awful much like this perfect square here did. It only had a plus. So that led you to think, well, that may be the perfect square of this very thing here, but with a plus in there. And sure enough, that was a perfect square of that. So if you have a square root of a perfect square, you lose that. That's all you integrate, and that integration is not too bad. Power rule here, power rule there. Then the messy part is substituting in your values. And that did get a little messy, but quite doable. Any questions on that? All right. Let's go to, example 3. If you have no questions on example 2, I've got to clear the drawing. Are you okay with that? Anyone still writing? Okay. So I'm going to clear this, and let's do example 2. Find the arc length of the graph of, ooh boy, this is interesting, y minus 1 cubed is equal to x squared. Okay. On the interval 0 to 8. Okay. Now, let me point out a few things to you. First, looking at the function, I don't know about you, but it looks like to me that's going to be a little bit easier to solve for x than it would be to solve for y. Okay? So if you did that, you can do it because they gave you a formula that worked there. But when they say on 0 to 8, those are values for x. So now you might be in a little bit of a quagmire here and say, which way do we need to go on this? Do we make this y as a function of x, which is a little bit messier, and keep our x's here, or do we do x as a function of y, which is going to be a pretty easy thing to do, but then we have to change our limits to represent the limits on y. Now, actually that last is not going to be so awfully bad, and here's why. So you see, I'm leaning toward writing this as a function, x as a function of y. When x is 0, put a 0 in here, y would be, if that's a 0, y is going to have to be a 1. So the interval on y would be going from 1, 2, and when x is 8, 8 squared is 64. Well, the cube root of 64 is 2, right? No, I mean 4. Okay? 4 times 4 is 16 times 4 is 64. So what's in here has to be equal to 4. So y minus 1 is 4. Y would be equal to 5. Okay? Oops. That would be our limits on y. So if you re-express this as x is equal to y minus 1 to the 3/2 power on this interval of y. Okay, so these are your y values. Okay, we don't usually write it that way, but that's what it would be. All right, well, let's see what we're going to do. First thing we do is need to take dx dy. Not used to doing that, but that's what we're doing. Dx dy would then be 3/2 times y minus 1 to the 1/2 power, right? And that's it. Then we got to square that. So if you square this and square this, what you get is 9/4, because you square that numerical part, times y minus 1. Hey, that didn't come out too badly. Well, let's rewrite this as 9/4 y minus 9/4, then add 1 to it. Add 4/4 to it. Okay, and that gives us 9/4 y minus 5/4. Okay, wait a minute. Sorry about that. I took the square root too soon. Back off. I knew I was going to get myself in trouble by skipping some steps, and I did. Let's back off here. What we did here was right, I'm pretty sure. I don't think I took a square root yet, did I? You squared this, and that's when you got 9/4. I was doing it right, sorry about that, times y minus 1. Okay, that's that thing squared. Add 1 to it, so I was right. Let's make that, I'm sorry, thought I was right, but then I got to second guessing myself. Minus 9/4 plus 1, which is 4/4, and this gives you 9/4 y plus 5/4. No, minus 5/4, sorry. Wait. Okay. I may be beginning to regret what I just did. Okay? Because then what you have to do is take the square root of this. Okay. Now the good news is you can pull out the 1/2, because you have a common denominator of 4. Square root of 4 is 2, so that would be 1/2 times the square root of 9y minus 5. And that's what we want to take the integral of, I think. So I may have made a bad choice coming this way, but let's see what happens. Be the integral now for the y's, it's going to be from 1 to 5 of, let's take the 1/2 on the outside, and this will be 9y minus 5 to the 1/2 power dy. Okay? I think this is doable. Okay? Let u substitution here equal 9y minus 5. Okay? Then du is equal to 9 dy. Right? Well, we don't have a 9 dy, we just have a dy, so let's divide everything by 9 and take it. So this would then be 1/18. You pull out the 1/9 and combine it with the 1/2. Now we have to change our interval here again. When y is equal to 1, that would be 9 minus 5, that's going to be 4. U would equal 4. When y is equal to 5, 5 times 9 is 45, minus 5 is 40. So 4 to 40. Okay, that's going to be the limits on u. And what we have here then is u to the 1/2, because this is your u to the 1/2, and then we have our du here because we already pulled the 1/9 out front. And this is doable. Okay, and this will be, I don't know where to write it, 1 over 18. Okay, and the antiderivative of this would be u to the 3/2 times 2/3, right? Antiderivative of that, increase that by 1, good old power rule, divided by 3/2, which is multiplying by this. Well, I'm going to do 2 into 18 will be 9, so this gives me a 1 over 27 on the outside, and on the inside we're going to take the square root. We're going to do 40. We're going to do the square root of 40 cubed. This is where it gets a little messy. Minus the square root of 4 cubed. Okay. I think I will do the cube here too. Okay. Boy, this part's always worse than the integration, isn't it? So this is 1 over 27. Now let's see what we've got here. Square root of 40, well, 40 is 4 times 10. Square root of 4 is 2, so it's 2 root 10. And that we're going to cube. Okay, minus, in the square root of 4 is 2. 2 cubed is 8. Okay, why they pick such weird numbers, I don't know. 1 over 20. I may have made a stupid mistake and gotten the numbers this weird. Okay, so this will be times 2 cubed is 8 times 10 cubed, the square root of 10 cubed. Square root of 10 squared is 10, so that'll make that 80 times 1 more root 10. Okay, minus 8. Yuck. Okay, I don't know what happened there, but it did. I don't know. Y'all may not have seen anything. Okay, now that's an odd answer. I don't know. Did I get it right? 1 over, guess what they did? They left it as 1 over 27 times 40 to the 3/2 power, which is exactly what I have down here. 1 over 27 times 40 to the 3/2 power minus 4 to the 3/2 power. That's exactly what I've got. And then they do an approximation of what that answer is. Well, I'll pull out my calculator and see if we get the same thing. Okay, it's actually my phone. I don't know what that was, some sort of garbage, I think. So let me get rid of that. Okay, let's find my calculator here. Okay, now the way I did it up there, I'm going to divide by 27 at the end. So I'm going to turn my phone that way so I get scientific mode here. And I have 80 times, now I'm going to open a parentheses. I tried to open a parentheses. I can't tell, I probably opened 2 then. Let me start over. Okay. 80 times, open parentheses, 10, close parentheses and take a square root of that, minus it didn't work. I don't think it did. Minus 8 I'm going to divide that by 27. No, I don't like my phone as a calculator. The main reason, it had little bitty buttons. I have great big fat fingers and they just don't match too well. So let me try that again. 80 times, open parentheses, 10 close parentheses, square root. There, it worked that time. Minus 8. No, it's not working. There's still something wrong here. I don't think I closed my parentheses. Let me just try it brute force without. 80 times 10 square root minus, yes, that's working better, 8 equal, and then divide that by 27. 9.073. Yes, that's exactly what they got. Okay. So, yeah, my answer is same as theirs, which I think you probably figured it was. You better have figured it was. Okay. So, messy, messy problem. Just getting things that you can integrate nicely, we usually will mess up doing evaluation, especially if you choose intervals like, well, that one wasn't too bad, 0 to 8. But now they didn't do it my way. They did it the DX way. And let me just show you how that would have worked. Still would have been all right. Okay. What they did is take a cube root of both sides, and that gives you y minus 1 is equal to x to the 2/3 power. Okay, and then add 1 to both sides, you get y is equal to x to the 2/3. That's supposed to be a 2/3. It's really writing poorly. Plus 1. Okay, and then you proceed and take the derivative of that, and that wouldn't have been bad either. Okay, I'm not going to say it's any easier than the way we did it, but it works too, and they got the same answer. Okay, so that one could have gone either way. Solve for x, solve for y. Okay, they're both pretty straightforward after that. You still run into the same mess at the end, though. There's no way to avoid that. All right, let's move on to example 4. Any questions on 3 before we delete it? Okay, so I'm going to clear the drawings. I got to get the book in my lap. I just can't see that far over there. Okay. Oh, here's an interesting. Okay. Find the arc length. And by the way, this one's also located at larsoncalculus.com. There you can see an interactive version of this type of an example. Not a bad idea. What we want to do here is our function. I told you they had to come up with weird functions. Here's one. Y is equal to the log, natural log of the cosine of x. Now, I would have griped and hollowed about them writing it this way because they probably needed to put it in absolute value bars until they say from, and I'm just going to do it. I'm going to put on. Now remember, this is talking about the values for x. X is going from 0, and cosine of 0 is 1, so that's all right, to pi fourths. Well, cosine of pi fourths is root 2 over 2. So those are both positive values. So now, yes, you could have left that in that. Okay? So your cosine is positive everywhere there, so you don't need the absolute value bars. But it's only because of that. Now, I'm not about to graph this for you, but I'll show you how it graphs. And if you think about it, when cosine of 1, when x is equal to 0, cosine is 1, log of 1 is 0. So it starts at 0, and then when x is pi fourths, cosine of that is root 2 over 2, which is about 0.7. Log of a number between 0 and 1 is going to be negative. So sure enough, this function starts at 0 and goes negative, and that's what it looks like. And they only show it from negative pi halves to pi halves because that's as far as it can ever go. It can't ever reach 0 on either end. So that's what, but we're only interested in 0 to pi fourths. So that's the graph we're looking at. Not a very long curve, obviously, so I think we can handle that without too much problem. Okay? Now, so what do we do first? We've said it several times. Take a derivative. Y prime is equal to, and what is the derivative of a log? 1 over the argument here, cosine x, times derivative of cosine x, which is a negative sine x. Okay, and if you look very carefully at that, that becomes negative tangent x. Okay, the pen's not writing too well. Okay, now what do we do with that? We square it. When we square it, we get tangent squared x. That's not too bad. Okay, then what do we do with that squared? We add 1 to it. All right. Well, what is tangent squared plus 1? From your Pythagorean identities back in trig, I hope you remember well, tangent squared x plus 1 is secant squared x. Then you take a square root of that and you get a secant x. So what is your arc length? S is equal to the integral from, x is going from 0 to pi fourths, not too bad of an interval there, pretty short, about pi fourths, don't change the 4 to a 2, okay, of square root of secant squared is just secant x dx. Now, what's bad about this problem, it was going so nicely, is what is the integral of a secant x? It's a weird integral, okay? And what I would recommend, because I don't memorize these things, I don't like memorizing these things, if you go to the front inside cover of your text or any integration tables you may have handy and do the integral of secant x, you'll see that that turns out being, believe it or not, the log of the absolute value of secant x plus tangent x. Okay, and we're going to evaluate that from 0 to pi fourths. Okay, now we won't need the absolute value bars, I don't think either. Alright, so let's figure out what this is. Log of, I'm going to change it to parentheses, secant of pi fourths. Remember, secant is 1 over cosine. Cosine of pi fourths is root 2 over 2, which you could have expressed as 1 over root 2. So this is just going to be, and secant is 1 over that, so this is just going to be root 2. Plus, oh wait, yeah, plus the tangent of pi fourths is 1. Okay? Minus, when you do the secant of 0, if you recall, that's 1, because secant is where 1 over cosine, and cosine of 0 is 1, so secant is 1. So those are going to disappear. Okay? If I can find my pen, where did it go? There it is. Okay. And then tangent of 0 is 0. So basically, there we got it. Log of root 2. Now, that's probably a perfectly good answer. You could have written that as log of 2 to the 1/2 power, and that you can then say is 1/2 the log of 2. And you don't need absolute value bars because those are positive numbers. So either way you want to do it, that's it. Let's pull out the calculator and see what the 1/2 the log of 2 is. Okay, I'll turn my calculator sideways so I can do the thing. So I'm going to do the 2 first, and then the ln key. That's how I have to do it on mine, and then divide that by 2. And that gave me 0.346 blah 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 blah. And what did they get? Oh no. Okay, I've done something dumb here, but I can't figure out what it is. Oh, I know. Yuck. Here's what I did. I put my limits on this stuff, and it wasn't on this stuff, it's on the log function. So this should have been minus the log of 1. No, yeah, that's it. Okay, so those didn't cancel out. Log of 1 plus 0, which is 1. So sorry about that. This is, the answer is log of root 2 plus 1 minus 1. Because, minus 0. So log of root 2 plus 1. So that's where I messed up. Sorry about that. So it's 2 square root plus 1 equal, and then take the log of that one, and you get 0.88 something in there. Yeah, 0.881. Yeah, sorry about that. This is about 0.1. So here's, let me see if I can clean up my mess here. Okay. Okay. It's the log of this minus the log when you put 0 in there. I left off my log here. And when you put 0 in here, this, let me get rid of my eraser, or else when I touch the screen I'm going to erase something. That would be log of, let me also get rid of this, sorry. This extra parentheses is not necessary. Okay. Okay. It's the log of root 2 plus 1 minus the log of 1. Secant of 0 is 1. Tangent of 0 is 0. Yuck. Okay. So, I guess probably to make sense here, let me also get rid of this little squiggle. Okay. And then we said this is approximately equal to 0.88 something another. They said 881. 88 is fine. Okay, sorry about that. Because the log of 1 is, of course, 0. So it's just log of this. I thought I erased that. I'm pretty sure I did. And something decided to go on and put it back in again. So let me erase. Yuck. erase that again. Okay. Now, this line is not any good anymore. Okay, so there we have log of this because this is 0. Whew, finally got it right. All right, so that was example 4. Like I said, coming up with the equations of the work is still going to probably wind up giving you some really hairy looking things to evaluate, but at least you can integrate them. So now we go to example 5. This is length of a, any questions on this one before I erase it? Okay, y'all are not speaking up very fast, so I'm going to go on and erase. How are we doing on time? We've got some time here. An electric cable is hung between 2 towers that are 200 feet apart. Now, I would just as soon not have to draw this graph. So I want to show you their picture. I can't draw it that pretty anyway. Okay, now notice what they did. They took the y-axis and made it directly between the 2 cables. So that made them 100 feet on one side or another. Okay, so there's the first part of the problem. Electric cable is hung between 2 towers that are 200 feet apart, shown in the figure. The cable takes the shape of a catenary, whose equation is, okay, now this I'll write out for you because it's not something I want to remember, but I'll write it out for you. Here's the equation for that catenary. Okay, and they're giving you this, so all right, y is equal to, now in case you didn't pick it up, the towers, they didn't say this, but the towers I think are 75 feet tall. Okay, they don't ever actually say that. No, they're not 75 feet tall. Okay, here's just the formula. Okay, I can't give you any rationale. I'm just telling you this is what they're giving you. 75 times e to the x over 150, okay, plus e to the x minus x over 150. I can't get this stinking thing to write. Okay, trying to write a minus sign. Okay, that's an ugly minus sign, but it'll do, over 150. Okay, now they go and get into cosecant, hyperbolic cosines. We don't want to do that. We're going to use this, okay, because what they're going to do is turn right around and go back to exponentials because they're so much easier to work with. Now, here, that is the equation of the catenary. If I'm understanding their figure correctly, then it looks like to me that 150 is the lowest point that the catenary has to the ground, is 150 feet. If I'm understanding their picture right. So that's where they get the 75 is half of that. There's no real reason why they give you that as that, but that's what they got. They write it in terms of hyperbolic cosine. Don't mess with this. Leave it in this exponential form. It's so much easier to deal with. Okay? So there's your y. Okay? Find the arc length of the cable between the 2 towers. Okay? Well, first thing you got to do is take a derivative, of course. So y prime is equal to, let's take the 75 on the outside. Don't mess with that. Derivative of this is e to the, I think that's an x there, x over 150. Okay, derivative of an exponential is the exponential, but then the chain rule would put you 1 over 150 here. Okay, and then you would say a plus here, the derivative of this, but its derivative is going to be negative. So that's going to be minus a 1 over 150 e to the minus x over 150. That time it wrote the minus sign very nicely. Okay, so there's your derivative. What do we do with the derivative? Well, before we do anything for the derivative, let's factor out the 150s. Okay, well, 75 happens to be exactly half of 150, so this would be a 1/2 out in front. And what we have on the inside would then be e to the x over 150 minus e to the minus x over 150. All right. Now what's the next thing we're going to do? We're going to square it. Okay. So this will be a 1/4. And then when you square this, you'll have this squared, which will be e to the x over 75. Oh my goodness, there it shows up again. Because when you square this, you double the exponent, and that gives you that. Minus twice the product of the two. Well, the product of the two of these is 1. Because this is x to the minus that, that's x plus this, that's x to the minus that. Product is 1, twice that is 2, so it's going to be a minus 2 plus, because you're squaring this one, and that will be an e to the minus x over 75. Whew. Okay, so there you've taken the derivative, you squared it. Now you add 1 to it. Okay, now before I do that, I'm going to go back and put this in like this. E to the x over 75, and then I'm going to do minus 1/2. Wait a minute, I've messed that up. This is over 4, so maybe I don't want to do that. Yeah, I think I do. Okay, plus e over 4 to the minus x over 75. Okay, so this is the same as that. I just multiplied the 1/4 times every term there. Now to that I'm going to add 1. Well, of course that 1 is 2/2. Added to this will make it plus 1/2. And now, just like before, we look at that and say, hey, that looks like the perfect square of what we had here. Before we did this, it looks like the perfect square of 1/2 e to the x over 150, going back to this, plus e to the minus x over 150. Okay, when you I'm taking the square root of this thing, and just like when you squared this, you got that. When you square this, you'll get that. Okay, check it out and see that's indeed what you got. So this is the thing we're integrating. I'm going to take the 1/2 on the outside here, the dx over here, and x is going from minus 100 to positive 100. Now the only question I have, in looking at the graph of it, that looks like it's exactly twice, so I'm actually going to make this 0 and double this, and you get 1. So let's do this integral, and that's going to be the antiderivative of that would be e to the x over 150 times 150, okay, minus e to the minus x over 150 times 150. So I'm going to take this and put it there. So the 150 comes out front. Whew. I hope I've done it right so far. Evaluate that from 0 to 100. Okay. Well, 100 over 150, that's the same as 150 times e to the 2/3 minus e to the minus 2/3. Okay, and that's just a calculation. So let's pull out our handy dandy calculators again, and let's see if I did it right and didn't make another dumb mistake. Okay, got to turn it sideways because got to get in scientific mode so I can do the e's here. So I've got to first do 2 divided by 3 equal 0.66667. You know, you got that. Raise that to the e power. Okay, I get a 1.94 blah blah blah, 1.95 almost. Okay, now subtract from that and now I've got to do, I think I'll do a parentheses here. It messed me up last time. Parentheses 2 divided by 3 close parentheses, negate, and do an e to that, and that gave me a 0.513. Press equal and multiply that by 150, and I got something like 215. Yes, 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 that's the answer they got in the book. Something close to 215 feet. Okay, now let's see if that even makes sense. The towers are 200 feet apart. You've got some dip in it, so the line between them you would hope to be, well, it has to be greater than that. 215 feet does give you the right answer. Like I said, they'll go to all kinds of mental gymnastics here to come up with weird looking equations and formulas that you, when you take a derivative of it, add 1 to that, square it. No, take the derivative of it, square it, add 1 to that, then take a square root, that you come up with something you can integrate. And sure enough, here we did, and they happened to choose numbers that made it not too easy, not too hard to evaluate. So they come up with some weird answers, but they weren't that hard to evaluate. So that leaves us 5 minutes. So let's now move to, any questions on this one before we leave it? I didn't write my answer down, but this is approximately 215 feet, if you do need that later on, okay, to do your evaluation. Most calculators will do those evaluations a lot more neatly than the phone does. Okay, so let's go back to the PowerPoint, and in 4 minutes, now here is, okay, resume slideshow. All right, now we're moving on to areas of a surface of revolution. Okay, now I'm going to plug in my phone. I don't think I'll need it in the next 4 minutes, so the way it'll be charging. Okay, let me get a drink of water too. Wow. Okay. Here's the definition of a surface of revolution. When the graph of a continuous function, now we're also going to require it to be a smooth continuous function, but right now all they're saying is a continuous function, is revolved around a line this way or this way. Okay, sounds familiar, doesn't it? Resulting surface is a surface of revolution. So we're not talking about volume now, we're talking about the surface area of that surface. So the area of a surface of revolution is derived from the formula for the lateral surface area of the frustum of a right circular cone. Boy, aren't those some fun words. Okay, here's what we mean. Now they spend so much time on the frustum of a cone, it seems like they could just go away with this, but it's okay. Consider a line segment in this figure here where L is the length of this segment right here. Okay, R1 is the little radius at the left hand end, and R2 is the big radius at the right hand end of that segment, because L is an increasing function here. You're revolving around this axis of revolution, wherever that happens to be, and this gives you not a cone, but the frustum of a cone, meaning it's truncated at this end. This would be fine as the base, but you've left off the top part of the cone. So this is the frustum of a cone. Not that you really are going to need that anymore. When that line segment, that one we had right here, is revolved around that axis of revolution, okay, it forms a frustum of a small, okay, so now the surface area of that would be 2 pi r. Now what is that r? They haven't mentioned that. We're going to get to it in a minute, times L. Okay, now what the r is the average between these two. So basically this midpoint right here, if you did right up to there and then flatten out the L, okay, that would give you, do that around there, that would give you exactly the same area, surface area. So that's what you get, 2 pi r, where that r is the average between these two going around the axis of revolution. That would be the radius of that midpoint there going around there. That would be 2 pi L. That would be exactly that, 2 pi r times L. 2 pi r times that length L. Now that r is the average between those two, the average radius of the frustum. And again, whoa, is that a chat for me or for someone else? Because I think we got everybody here, don't we? Yeah, it was perfect attendance. So I don't know what that was. Someone sent a chat to somebody. Okay. Now, let's consider a function f that has a continuous derivative on the interval a to b. Remember before it just said continuous function, now it has to have a continuous derivative on the interval from a to b. Here's a, here's b. There's your f. Nice smooth curve. The graph of that revolved around, say, the x-axis or any other horizontal axis there to form the surface of revolution as shown here. Looks like a cup or something like that. Pretty nice looking shape there. Okay, now if you took any interval of that, you approximate that by a frustum of a cone. And here's why it's not going to make any difference on what those radii were, because guess what? You're going to let that delta x get smaller and smaller and smaller until you only have that f value there as being the radius. So why did they mess with the big radius, little radius, take the average? You're going to have this approximated by very, very small delta x, and that will be the radius then would be your f at that point, and that's what you're going around. So I've almost given it away already. Okay? Let delta, how are we doing on time? 3 minutes? No, we just went over. I'm sorry. We're going to have to stop there. Sorry about that. Where are we here? I don't even see where we are. Where is that partition be? Oh, there it is. Okay. We'll start right there on page 478. Now, did we get far enough to do some homework? You bet we did. Okay. So homework exercises here would be number 5. Any of the odds 7 through 19. There, 5's at Calc Chat. All of 7 through 19 are at Calc Chat. 7's at Calc View. Okay. Then do any of the odds 21 to 29. They're all at Calc Chat. 31 should be at Calc Chat. 33, very similar to one we did in the book, that should be at Calc Chat. Okay. 35 should be at Calc Chat. So let me back off and say any of the odds 33 through 37. Okay. They should all be at Calc Chat. We'll pick up the rest of those next time. Any questions before we leave? All right. Good deal. And this being a Wednesday, I guess I say have a good weekend. And of course, working on calculus would make it a good weekend. All right. Seems like we've lost somebody, so someone must have just checked out. I'm going to stop the sharing. Do y'all have any questions, issues, or concerns before I end it? All right. Good deal. Have a good weekend. We'll see you Monday. Okay? Bye-bye.